Hello, Mr. Purito. This is the President speaking. The time has come. Earth has about 50 years left before it becomes inhabitable. We need to launch Project Crappy and terraform Mars as soon as possible.
Yes, Mr. President, yes, I'll get it done, sir. Join us. Bad news. We've been assigned to Project Crappy. We need to get it done real quick. This is top priority. I know we don't have a lot of time, money, or resources, but I told the President we'll get it done, and we will get it done.
Yes, sir. I know the right people for this job, sir. We'll get this up and running in no time.
Well, the whole idea was to improve upon a previous design that we designed around half a year ago. And however, that design proved to be ineffective at certain tasks, particularly automation and exploration, for which this new design would have to be very good at. And so we had to improve on all of these. Obviously, we had to recruit the best in the field to achieve these goals. And so the design of Crappy was obviously inspired by the previous rover, but with the main improvements of us trying to achieve automation and object manipulation and autonomous navigation. This time around we tried to use PETG plastic for parts that we deemed would be under higher stress than usual. And so we replaced several parts on the rover with these stronger parts. We also improved the design of the robotic arm, which last time was proved to be ineffective. Now we have, or we should have, a robotic arm that can successfully manipulate objects and place them in an internal storage compartment for further analysis. We designed this internal storage compartment to be housed underneath a tiltable solar panel, which, in combination with the rotation of the rover itself, can be used as a two-axis mount to optimize solar charging capabilities. Additionally, we added a thermal camera, an infrared camera, and a LiDAR sensor on top of the sensor mast. This would allow us not only to create a better view of the environment as the rover was exploring, but also to map as we traveled.
Yeah, when the director of NASA called me, I was absolutely intrigued. This is a very top secret and demanding project. It's very difficult. Some people have said it's impossible, but when they called me, I knew they called the right man. I look the challenge straight into the eyes and say, bring it on. Throughout the project, I was in charge of enhancing the robustness of the rover. The method of choice was to exchange the PLA pieces with pieces made out of PETG. PETG is a much tougher material than PLA and was the material of choice for our parts. Under my supervision, a total redesign of the arm was conducted from the ground up. The arm features now 5 degrees of freedom, allowing it to rotate and move around in all ways necessary. It features a gripper at the front, which can pick up objects from the ground, which dramatically increases the ways in which our rover can interact with its environment. Absolutely wunderbar.
The soul would need somewhere to be held and discarded once the arm picks it up, and so a collection tray was designed. There were many ways to go about this, and many prototypes were created in order to come up with the best design that would provide maximum efficiency. For instance, the first concept of the collection box was to use a sliding crank that would push open the bottom door of the box, and then it would let out the soil when no longer needed it, or keeping it closed and sliding back from an open position.
Well, compared to the previous model, Crappy now has 7 types of working sensors. We have added 5 modules to collect ultrasonic data. So basically, the rover can detect objects nearby, and depending on the amount of time that it takes for the ultrasonic wave to come back, it can calculate the distance from it. This was done with the aim of guiding the rover and avoiding any possible collisions. We have added also a gas sensor that has the ability to detect concentrations of gases such as LPG, methane, propane, hydrogen, and carbon monoxide. Then we also have two more sensors that have the ability to collect data from the environment, such as temperature, humidity, pressure, and relative altitude. All these variables contribute to the collection of data to make sense of the environment. However, we're also interested in the soil that the rover walks in order to have a complete picture. So we have also added a soil moisture sensor that allows to get an insight into whether or not we can find water on another planet. When collecting all this information, it is important to know where the rover is located at all times. So we have worked on a proof of concept for a GPS navigation system. This module would record the coordinates of the rover and would allow us to create maps of where the rover has been found, which is a feature that can be used on a local area using pseudo-satellites. Finally, we included a radio frequency transceiver, which would allow to send data wirelessly and monitor remotely.
The addition of the sensors wasn't the only notable improvement from last time. We designed a sensor head to elevate the entire mast to a significant vantage point. This was not only necessary so that the thermal and infrared cameras could have a better view of the surroundings and could see further away, but also would allow them to be used as a diagnostic tool. The cameras, capable of tilting and panning, could be pointed to different parts on the rover to see how the other modules were coping with the strain of the experiment. Furthermore, the vantage point allowed us to mount the LiDAR higher up, giving it an unobstructed 360-degree view of the surroundings, something which is critical for LiDAR operation. This would allow us to create a 2D point cloud of the surroundings and therefore create maps of the environment as we were travelling along.
Well, this rover wouldn't be very useful if it was only plastic and metal. So we have made some major upgrades in the software capabilities of the rover. As for rover, it still relies on the Raspberry Pi running its computing power, but we have made some major updates in the web interface to control it. So unfortunately, we haven't managed to implement autonomy to the rover, and so this is the reason why we are using a web interface to control the rover and to get data from it, because the implementation of the genetic algorithm, as we'll see later, was kind of challenging. So this time, instead of having only the controls on the web server, we have implemented multiple different capabilities, like reading sensor data, controlling the robotic arm, reading the ultrasound sensors.
So with the team, we designed a program that could take the data through serial connection from the Arduino onto the Raspberry Pi. This data was then stored on the SQLite database into different tables, one for the GPS data and one for the sensors data. The sensors data table was then converted into a JSON file, which allowed us to upload the data onto the Flask app. Through the use of the charts.js library, we were able to transform the data from numbers into charts and display it on the web app. Now, the original idea of the project was to transfer the data, not through serial connection, rather through radio frequencies using radio modules. However, we found out that the presence of Wi-Fi's and other signals on Earth jammed our frequencies and so didn't allow us to have a clear connection between the two radio antennas.
So the original idea for this project was to achieve autonomy. And there's multiple ways to do this, but because of the weird geometry and the shape of the rover, the simple out-of-the-box software that we could use was not really available. And so we decided to basically create our own framework and our own modeling framework from scratch with using Python and JavaScript. Our rover has 5 ultrasound sensors which show 45 angle differences and allow the rover to detect distances. With this and the modeling software, we created many different states of the rover, and we just like threw them off with a neural network that was randomly generated. The ones that would do best in achieving the goal that was to arrive to the GPS coordinate that we gave would be selected and then mixed together to improve their traits and then create the second generation. This second generation would do the same, we select again, and we create the third generation, etc. With this method, we select for the best traits and the best faring rovers, meaning that they are the ones that have best avoided obstacles. And as such, with enough training and enough generations, we hope to achieve the actual automation of obstacle avoidance.
From a hardware perspective, the Crappy project can be declared a success. The robustness of the rover was improved, which is very important for a mission that takes place in a very remote location. Also, it's very nice to now have a functional arm on the rover, as it allows us to much more closely analyze the various materials that are present on the Mars.
When it comes to the sensor design, we were successful in giving the rover all the tools necessary to evaluate its environment. From the thermal and normal camera to observe Mars surface, to the modules that analyze the atmosphere and environmental surroundings.
Although we were able to generate 2D point cloud data from the LiDAR, the algorithms required to process this constantly refreshing data into a static 2D map were significantly more complex. Unfortunately, we were unable to implement algorithms such as pose optimization and simultaneous localization and mapping, given the time frame. However, considering this is a software obstacle, we hope to have it up and operational by the time the rover makes landfall.
Yes, Mr. President. Yes, good news, sir. We were able to implement the genetic AI algorithm. We implemented the LiDAR and the cameras. We have a fully functioning robotic arm, and all of it, sir, can be controlled from a web app. All the sensors can have their data analyzed, and you can control everything and see the live stream, sir. I think Project Crappy will be a huge success, sir.
Yes, President. We have worked very hard for this last month on this project, and we have made major leaps forward, even though not as much in autonomy as expected. However, the team worked hard, and I think we can call this a success.
Ground control to Major Tom. Ground control to Major Tom. Lock your Soyuz hatch and put your helmet on. 10. Ground control 9, to Major Tom. 8, 7, 6. Commencing countdown, engines on. 3, 2. Detach from station and may God's love be with you. This is ground control to Major Tom. You've really made the grade, and the papers want to know whose shirts you wear. But it's time to guide the capsule if you dare.
Have you ever felt the hardship of grabbing a hanging towel, or the quagmire caused by that cup of coffee just out of reach?
Well, suffer no more, thanks to the latest and improved version of the Crappy rover. It can lift those towels and bring you your coffee in the morning without any struggle. It is discreet, agile, and precise, and will satisfy all of your needs.
Text Crappy to 1888-CRAPPY to learn more and get yours to help you with your daily chores.
Comes bundled with a meteor station and GPS.